We're going to have Samson talking to us about Domain-Theoretic Semantics for functional logic programming. Yeah, feel free to start.
Thank you. Okay. Wonderful. Thanks so much. Good morning. So our paper, we present a functional logic programming language and do some denotational semantics on it and various analysis of it. So to first provide a common ground of what we mean by functional logic programming, I thought we'd just go through a very simple example, quite a well-known example. So we've got this program here, last, which hopefully it's quite clear, computes the last element of a given list. There is no recursion. Instead, we declare two variables, x's and x, and we take our input y's and equate it with the concatenation of x's and the singleton x. And then if we just if that is successful, we can return x to obtain the last element of the list. So this example quite clearly demonstrates what we're interested in. First and foremost, it is a functional programming language which we extend with features inspired from logic programming, namely non-determinism, logical variables, and equational constraints. Non-determinism being necessary because there could be more than one solution, or you might have to consider a bunch of solutions to continue evaluating. So FLP itself has quite a long and rich history. We've got this review article here, which just provides a general survey of it. I think it was published in 2010, so many years ago. Unfortunately, there hasn't been an adequate and fully abstract denotational semantic which, for a language which supports the three main constructs that we're considering. So regarding what we present, we first introduce a typed call calculus based on call by push value. And we're able to do this because we understand the effects we're adding on top of our functional language as algebraic effects. So we can take full advantage of call by push value to do this. We present an abstract machine based upon Staten's algebraic theory, which is it's an algebraic theory from an algebraic presentation for predicate logic. It's the title of the paper. We then examine domain-theoretic denotational semantics, in particular using the lower power domain. And then we examine a specific model which we show to be adequate and fully abstract for the abstract machine. However, it's only relative to a termination-insensitive notion of program equivalence. So we can have two programs, and if you just take the same program, then once it's finished evaluating, you just run a program which diverges. Unfortunately, our model will say that these are the same program, and obviously this is a shortcoming. Regarding how we can actually fix this, we examine what is necessary for a domain-theoretic model to be able to distinguish failure in order to be able to model this termination property that we seem to be interested in. So regarding the types of the language, we've got all the usual stuff. It's called by push value, so we make a distinction between value types and computation types. Value types not having an underline underneath them. So you can, in call by push value, you can always go between value types and computation types via funcs to go from a value to a computation, and, returners to go from a value to a computation, and funcs to go in the other direction. And we also single out a collection of what we call first-order types. Now, if you have a quick look at them, you can see that these are exactly the value types which are not funcs, or don't contain a func anywhere in the syntax. And so what this means is they were never at any point a computation. So here's the call calculus. So for instance, if you want to make a natural number, there are only three laws that you can use to do this. It's either going to be a variable, zero, or successor. And so if you actually want to do something with this, with a natural, you'll first have to return it to turn it into a computation, and then you can proceed from there using bind and, for instance, if zero, if you so desire. We've also got fix here, quite unusual. So variables in call by push values always refer to values. So in order to define something like fix, you would have to use a func on the computation that you are trying to define recursively. So we've also got typing judgments for the effects that we're interested in. At every computation type C, we have a judgment for failure. We're able to combine two computations to give non-deterministic choice. And we can also quantify it over a variable in order to to define exists and equate two values, and then proceed evaluating a computation. Note that we use sigma in the judgments of exists and equate. The idea is that we can only quantify over first-order values, and the reason we want to do this is because these first-order values have a very nice inductive structure that we can use in the evaluation strategy when we actually want to run these programs. So regarding the abstract machine, we take the CK machine, which just consists of the computation and the stack on this diagram. And we append a context gamma, which will contain our logical variables. And the idea is that as you evaluate a computation, you accumulate these variables throughout the execution. So what this means is that if you start with a closed computation M, as it evaluates, it might become open. It will always be closed with respect to gamma, but as a term on itself, it might be open. In order to perform narrowing, we use what we call a weak head narrowing strategy, which is is inspired from what is known in the literature as needed narrowing. So here is a short example, or a short collection of our effect-free transitions. If you want to evaluate something which binds a computation, you first push the continuation of the stack, evaluate M. If M doesn't diverge, also doesn't perform any effects, then it will reduce to a computation or to a basic machine where the computation is return V. You then proceed by popping the continuation of the stack and doing the appropriate substitution. We've also got if0 here. It's very clear what to do when the value that you've got in your if0 is 0 or successor. But as I said earlier, the computation might become open. And so it could be the case that you are doing if0 on a logical variable contained in the context. And it's not exactly very clear what we should do then. Intuitively, we want to consider two cases, the only other two cases for a natural number that is not a variable, namely it being 0 or successor. But as it is, our basic machine can't handle this sort of non-deterministic behavior. So we extend basic machine to that of a configuration. The configuration itself will either be fail, some basic machine, or a choice of two other configurations. So you can imagine it's some sort of tree structure where the leaves are either failure or basic machines that are still evaluating. And then we can lift the effects that we have in our computations in order to define the transition relation. We just lift it to the level of configurations. So failure in a computation becomes failure at the level of configurations, and the same for choice. To deal with exists, so this is a quite clear example or demonstration of how a computation can become open. You simply push the logical variable that you're quantifying over into the context. So in order to deal with unification, we use the very well-known idea of a most general unifier. So we're able to do this because all of the values that we equate are first order, so the algorithm that does exist applies. And the intuitive idea is that you find the least, the formal definition is it is a substitution which will syntactically equate V and W. It being most general means that if you have any other substitution which equates these two values syntactically, it factors through the original substitution. And once you find the most general unifier, you apply it globally, both to the computation and the stack, and you also update your context of logical variables. Now, obviously, there could be cases where there is no most general unifier, for instance, if you equate 0 and 1, and in that case, we just return fail at a configuration and stop evaluating. So regarding this example, this is very motivating for the strategy we use of weak head narrowing. So we've introduced configurations, and now we're able to do something like this. We say that an abstract machine is blocked on a logical variable x if you cannot continue evaluating without knowing more information about x. And in this case, we continue evaluating by introducing the least amount of information we need least amount of information we know about x, namely it being 0 or successor. So you return a choice, x replaced with 0, removed from the context as well, and then x replaced with some fresh logical variable n, and x substitutes for successor event, or the other way around rather. And so, going back to this problematic example, we can continue evaluating like this, and it's obvious what to do now with the if0. So just a very short example execution of a program. So hopefully it's quite clear that this should give you some positive natural number, and you can follow through and check that each one is indeed correct. So in the end, we get return successor of 0, or successor of some natural number n. And a simpler program which does the exact same thing is to introduce two logical variables, n and m, such that n is the successor of m, and the transitive closure of this will give you successor of n as the resulting computation. So because all of our first-order values have an inductive structure, we're able to apply the exact same idea to them. So for example, with lists, you replace x with nil, or you conjure two fresh logical variables and consider cons of them. And we also have a completeness result. So results is something I will define later, but intuitively it's just, the final set of values you get at the end of running your program. And we say that if you have any value of the appropriate type, then substituting x with that value will never give more results than quantifying over a logical variable. So regarding the denotational semantics now, we have recursion, so we're going to need complete partial orders. Namely, all our value types will be complete partial orders. The first order value types will be discrete posets, discrete partial orders, which are trivially complete partial orders. And the denotation of computation types will be complete pointed partial orders, which means that they will have a least element. Now we note that in call by push value, effects only occur at computation type. So we just need to add some suitable algebraic structure to the computation types. So we have nondeterminism, which means that we are going to need some sort of join semilattice structure. If we have two elements in this domain, we should be able to return their join, which is the nondeterministic choice. But we also have unbounded nondeterminism. Because we quantify over naturals, for instance, which is an infinite data structure, it has infinitely many values, you can quite easily, especially in the presence of recursion, construct an example where we do an unbounded amount of nondeterminism. As such, it's not enough just to have a joined semilattice structure. We actually require a countably complete joined semilattice structure, which means not only can I take joins of finite sets, I can take joins of potentially countable sets. And so the question is, how do we combine these algebraic structures? One might think you can just use the power set in order to deal with this, but unfortunately it completely destroys the complete partial order structure you have on your terms. So instead, we use power domains, which is the domain-theoretic analog of the ordinary power set, and it preserves the CPO structure that we're interested in. So regarding the choice of power domains that we have, the most simple one is the Plotkin power domain. So we have this join symbol, which is a function of arity 2, and we require these algebraic equations, namely commutativity, associativity, idempotence. We've also got this symbol epsilon, which we use for failure, no results. And we require it to be a unit of the join. You can then consider more equations on top of these. For instance, if we add this equation here, x approximates x join y, quantified over all y, of course. Then we get the lower power domain, or Hoare power domain, where nondeterminism should be considered angelic. That is to say, more nondeterminism gives me more information. I can obviously do something quite similar, where instead I say x join y approximates x. And in this case, we get demonic nondeterminism, where more nondeterminism is bad. It's interesting to see how the unit epsilon interacts with these equations. Notably, in the lower power domain, you immediately get that epsilon and bottom being the least element in your CPO structure, are the same thing. We also note that neither the Plotkin power domain nor the Smith power domain actually support unbounded nondeterminism, which we need. As such, we are forced to choose the lower power domain. So regarding its construction, we take a complete partial order D, and we say that any subset S is Scott-closed if it's a lower set and admissible. So a lower set meaning it's closed downwards according to your approximation relation, and admissible meaning it's closed under directed joins. Any directed set contained in S, it should also be the case that S contains its least upper bound. Then you may form the lower power domain as the complete pointed partial order of Scott-closed subsets of D, ordered by ordinary subset inclusion, where we take the empty set, which is a Scott-closed set, as the least element. From this, we very clearly demonstrate how you can construct a denotation for every term in the language. It's quite involved, I won't go into it. But notably, we end up where the denotation of fail is the same thing as the denotation of any program which diverges. Again, this was forced by the lower power domain. So modeling the machine in order to assess how good our model is, we take a configuration, and you can consider the results of this configuration. So this triangle here, this thing here means that this basic machine on the left is a leaf of the configuration. We're interested in all the ones that have finished evaluating. V can be open, closed with respect to gamma, so the context gamma. So what we do is we consider all substitutions of the variables in gamma which close V, and that will give you all your results. You can then extend this to a closed program which does return things. We only do this for programs of type FA. And you start with the basic machine, no variables, no stack. And you consider all configurations that you go through as you evaluate this program. And from that, we can accumulate all the results in each configuration. So for example, it's quite clear that this program here should give you all the natural numbers as its results. We can then define a relation between terms, where we consider all ground context, that is a context such that when you substitute m in, its type will be of f sigma, sigma again being a first order value, and we say m approximates n, observationally approximates n, if the results of this, if this equation holds. Note that the relation is inherently termination insensitive because in the presence of non-determinism, absence of a value does not imply diverging behavior, which you would ordinarily have in the case of something like PCF. So termination sensitivity is something you have to build on top of this relation. So regarding how effective our model is, we have a complete equivalence between the observational approximation relation between terms and the approximation relation in our model. How we prove this, very standard. To prove the backwards direction, known as adequacy, we introduce two logical relations. Two, because we're in call by push values, so you need one for values, you need one for computations. And then we prove, you simply, well, it's not that simple, it's quite long. You prove by induction this following lemma, whose intuitive meaning is that the meaning of terms preserves the logical relation. It's very well known in the literature. For the forwards direction, our proof is quite elegant, made much simpler by the fact that we can demonstrate all compact elements in the model are definable by some term in the language. So regarding how well we can actually, can we actually construct a model that is termination insensitive on top of what we already have? And so we can say a model is failure discerning if the denotation of failure and diverge are distinct. And we argue that if it is not impossible, it is at least very difficult to construct a domain-theoretic model which is failure discerning, subject to a small set of what we argue to be very reasonable equations. So our first argument, if you consider this equation here, dead end, so I have some computation m. If I then bind it to a variable, and then proceed to do a computation which always fails, we want this to be the same thing as failure. And there's a very obvious practical reason for why you would want this to be the case. If you're actually going to go and implement this language, you'd want to do something like this. It becomes problematic, however, when m is a computation which diverges, because you immediately obtain that diverge is fail. But perhaps you might say this is the only exception to the rule. And then we say, well, in response to that, we have this second argument. So we have these equations here. We require failure to be a unit of non-deterministic choice. Now we require, if you quantify over a program which always fails, this should fail. This is even more reasonable than this one, because any practical implementation really should do this. And then finally we have this equation here which says if I quantify over a variable and then run m, it should be the same thing as a non-deterministic choice where I consider 0 and then quantify over all the natural numbers incremented by 1. If in addition to that you have that the denotation of exists, which I've labeled, use this variable here, if that is also continuous in regards to domain theory, then we are able to immediately conclude that your model conflates failure and divergence. And so as such, it seems to be quite a difficult problem to obtain a model which does distinguish these two terms. Thank you for listening. My references.
Thank you. Do we have any questions? Anyone who's ready, give a question.
Hi, thanks for A very interesting talk. So I just wonder, have you considered a variation on your language where the choice is not unordered, but it's ordered, and then have a construct that can take a bunch of choices and turn them into a list?
Sorry, what was that last bit again?
And add a construct that takes choices and turns them into a list. So you can reify the...
Yes. We did consider this, and it would just be a fundamentally different model, I think. At least you'd have to drop some of these equations, namely, as you say, the commutativity of non-deterministic choice. But then looking at the power domains that we're interested in using for the denotational semantics, it's required that choice is commutative, so our work doesn't really apply in this case.
Pity.
Hello, I'm Joseph Zulo from Purdue University. On this slide, we have that, so X is universally quantified, right? So we have that bottom join epsilon is by left unit, bottom by the right unit, or the other way, by right unit, bottom by left unit epsilon. So I don't see how they could ever be distinguished, assuming that bottom and epsilon are both units of join.
Right. So this, if you do plug in bottom here, you will get bottom. But then what you say about considering the other way around?
So if you use the right unit, then X is bottom. If you use the left unit law, X is epsilon. So equals bottom equals epsilon, no?
I don't think so. So you're saying if we use commutativity, you would just get bottom again?
Yes, because commutativity combined with the fact, I mean, I don't think you even need commutativity. Monoid units are unique, no?
Mm-hmm. Yep.
So I don't see how bottom and epsilon could ever be distinguished.
I think choice doesn't have to be strict. So choice doesn't have to be strict.
What does that mean?
So you don't need that bottom choose anything is bottom.
So bottom is not a unit of...
Not necessarily. If it's a unit, they're unique, they're the same. And that's characteristic of the lower power domain.
Okay, I see.
In other power domains, that's not true.
Okay.
I think we got one more question up here somewhere. Yes.
Okay, thank you for the talk. So I was wondering if you could justify the dead end thing a bit more, because from a traditional programming perspective, this is not a reasonable axiom, right? Like if M have some effects, including divergence, then I definitely don't want you to start optimizing away my stuff. Is this like a restriction of the language you're considering? Is this something about FLP generally?
It is just one of our arguments for why it's quite hard to discern failure. It is, in some regards, it can be seen as quite unreasonable as we've identified, but then we have this other argument instead.
Oh, so is it either one? Because I thought it was a combination of all of these, if you obey all of these equations. Because I would
Oh, sorry. This is one argument on its own. If you have this, you conflate failure and divergence. If that's not true, maybe you still have this, and same result.
If I can ask a quick qualifier, what justifies the existential one? Are all of your first order types inhabited?
Yes.
Okay, well, that does explain it.
Hi, thanks for your talk. I just have a I have a question and a comment. The question, I suppose, is, do you see this work generalizing to like a constraint programming scenario as opposed to just logic? So sort of broaden the set of constraints you allow to more than just logical. Do you see that generalizing to that scenario?
Do you mean specifically the equate judgment?
Yeah, yeah.
What would you mean exactly?
So for example, broaden that to allow maybe finite domain constraints on integers.
Sorry?
So allow, for example, to like broaden it to like finite domain constraints on integers, for example.
I don't think I'm familiar with this, unfortunately, but I'd love to chat after.
And a comment, I suppose, with this slide in particular is that in my work on search heuristics for constrained programming, we actually, like failure is not actually a unit of a non-determinism, because you might make decisions in the heuristic based on how many times you fail. And so I'm just questioning whether this is indeed like a sort of reasonable thing to want.
Yeah, certainly. But for an extensional model, one might argue this should hold. So perhaps you'd need some sort of intentionality to accommodate for this.
Right, thank you.
Let's thank our speaker, and we'll move on to the next talk.